Well, friends, today we are going to learn about capacitance. This is also a very important chapter in electrostatics, and we will cover our lecture like this. What is the capacitor? We will talk about what is the capacitor, then how it is charged, what type of capacitors are there, how we can arrive at the formula for finding out the capacitance, and if the capacitors are joined in parallel or series, then what is the formula, how we can find out the equivalent capacitance, and of course what is the energy stored in the capacitor, and then dielectric. If we introduce the dielectric substance between the capacitor plates, then what happens, how the formula changes, and atomic view of the dielectrics. We will see how the Gauss law is affected due to dielectrics. These all we will see. So this chapter will cover all these things. So let us see today what we can cover, and in the next lecture we will cover the rest of the things. So first thing is, what is the capacitor? Capacitor is basically an electronic instrument. It is basically an electric instrument to store charge. We have seen how the charges are created, how the charges, we have learned so many things about electric charges. But in this chapter, how we can store a charge, and this is all about capacitance. But what is the need to store a charge basically? Let us see what are the uses or why it is needed. You must have seen flashlight of camera. Flashlight, I am talking about flashlight, which when you click for taking the photos, then a very high luminous light comes and it falls on the object. So how it is? Because of the storing of charge. This flashlight works on this principle only, because whatever battery is there in the camera, that cannot illuminate that kind of high lumen light. So we use there the capacitor, which stores the charge. Once you click the camera, then a large amount of this current is flown, and this is how your flashlight bulb is on. Second example, you might have seen lightning. Lightning it is also because of the capacitance only, because here your earth, this is, what is this? Your earth, this behaves like a isolated spherical capacitor. Correct? So when there is a storm and all, the charge of this earth, this discharges in the atmosphere, and due to this lightning occurs. Third example we can see in the case of steam, you might have seen in the because of rubbing, charges are accumulated, and it is those charges they discharge, and you can see the spark. So these are the some natural examples you might have seen. It has got a wide ranging of uses in our electrical industry. So now let us go to the how it is charged. So let us understand how this capacitor is charged. Basically, this is the parallel plate capacitor. Capacitor is nothing but two plates are there. It can be of any geometry. Suppose this is plus and this is minus. This is also a capacitor. This is because plus Q charge is there and minus Q. This is also a capacitor. This can be of any geometry, but for understanding sake, let us see these are two metallic plates. They are joined with a battery with a switch. This is a plus sign, this is minus, this is the battery's terminal. This is having the voltage of V. Now, once you close this, what will happen? This end is at higher potential, and here before closing there was no potential. So what will happen? This is a plus terminal. The electron, it will start flowing to this terminal. Because this is a metal, so free conducting electrons are there. So the electrons will start flowing to this terminal. Naturally, since electrons have started flowing, so this will be positively charged. Now here what is happening? This electron has come to this terminal. Now this battery will do some work, and it will be, due to that work, this electron will go to this terminal, and it will go to this plate. And naturally this will be now negatively charged. This is the charging process. Once this switch is closed, and this process goes on till these plates are having the potential difference of V. Once this potential and this potential is equal, naturally this flow will stop. Correct? If you enlarge this plate like this, what is this surface? This will be basically equipotential surface. Phase of the plates, because here everywhere the voltage is same. Now when voltage this V is attained, the naturally flow will stop. These are positively charged, suppose plus Q. Naturally whatever electrons are going out from this, they are coming to this plate, so this will be negatively charged. So this is the process of charging the capacitor. This is a parallel plate capacitor. So it is very easy to understand, but we have to understand what goes into when the capacitor charges. Now let us go to the third types of capacitors. Types of capacitors, actually I told you it can have any geometry like this. Two charges of equal value, plus and minus, if they are spaced apart, some spaced apart, they behave like capacitor. But generally we use parallel plate capacitors. I told you this is nothing but parallel plate capacitors. Two metal plates are there. Then cylindrical like this. This is cylindrical type capacitors, where this inside surface, this is one plate, and other one is outer plate, and there is a gap between. Correct? Then spherical, in a sphere also one sphere is there. Inside this another sphere is there. So this is one sphere and outer sphere, and there is a gap between this. This is the outer surface of the inner sphere. This is the inner surface of the sphere. So this is also like I told you, this is your plus, here minus, like that. This can be plus and this can be minus, like that. Here this can be plus, this can be minus. So of course there is, just don't forget there is a gap in between, like that. Here the gap is there. There is a gap between two cylinders. Here gap between two spheres. This is the cross section area. So these are the basically commonly type of capacitors are used. Let us see what is basically capacitance. I told you that once, because of this voltage, charges are accumulated. Basically Q is proportional to V, or we can say Q is equal to CV. What is this C? This is called capacitance. Q charge was accumulated on the plates with the potential difference of V. So this is called the. Now let us see what is its unit. Unit is actually basically it is measured in farad. And this farad is nothing but 1 farad is equal to 1 coulomb per volt. This basically correct. This is a very great unit, so we can use it in microfarad also or picofarad also, depending on the situation. We have seen till now Q is equal to CV. But what is exactly C? We have to find out. But C differs according to the type of capacitors. So first take the example of parallel plate capacitor and let us find out how we can calculate the value of C. We have seen this our parallel plate capacitor as this. Correct? Here positive charge Q, negative charge minus Q. Let us make a, naturally this will be the electric field like this. Electric field is from positive to negative. Let us make the Gaussian surface. This is our Gaussian surface. And as per Gauss law, what we learned, our formula is epsilon 0 closed integral of E dot dA is equal to Q enclosed. This was our formula. Now in this case, suppose this is the parallel plate and this area is A. Correct? Then what will happen in this case? Epsilon 0 E into A. Suppose this area is A, will be nothing but Q enclosed, that is Q. This is in case of parallel plate capacitors. Another formula we have learned, Vf minus Vi minus correct. In our last video with respect to electric potential, we have seen this formula. Now let us modify this formula according to our need. Suppose this is I, initial point, and this is final point. We are taking the integral like this, means our ds is like this, means E and ds are both in opposite directions. So, and what about Vi? This Vf, this will be at higher potential, this will be at lower potential. So this difference, suppose if it is V, then this will become E positive, and if we integrate it, then it will be nothing but E into D. What is D? D is the distance between the plates. Correct? Any problem up to this? This is from the Gauss formula. This is from the electric potential, what we learned. So here V is equal to ED and E is equal to epsilon 0 AQ. So here we can write it as E. Suppose, let us take here V is equal to, suppose from this E is equal to Q upon A epsilon 0. Q upon A epsilon 0 into D, or we can write it as Q is equal to V epsilon 0 A upon D. What is this? So in case of parallel plate capacitors, your C is epsilon 0 A upon D. Means your capacitance is dependent only on the area of the plate and distance between them. If you increase the distance, capacitance will come down. If you increase the area, capacitance will go up. So this is the formula valid for parallel plate capacitors, and it does not depend on any Q, or it does not depend on any V. It is independent of all those factors. So it depends only on the geometry of the capacitor, means distance and area. This area is nothing but this area, parallel this equipotential surface. Correct? Now let us see how we can calculate the capacitance in case of cylindrical capacitor. So I told you cylindrical capacitor is something like this. Inside cylinder is there and one outside cylinder is there. Suppose this is of length L. And its area is, its radius is A. Inside the radius is A, and this outside this is B. Let us draw the cross section of this. So this is your outside cylinder and this is your inside cylinder, and there is a gap. This is your A and this is your B. So this is plus on the inside cylinder plus Q charge is there, and here minus Q is there. Minus Q is there, so naturally electric field will be like this. This is how electric field will be there. Again, let us suppose make this Gaussian surface like this, and its radius is R. So again, by Gauss law, Q enclosed, correct, or Q will nothing but epsilon 0 E, and what will be the area? Area will be the surface area of this cylinder of the Gaussian surface, means 2 pi r L. I hope there is no problem in this. Or E will be nothing but Q upon epsilon 0 2 pi r. Now what is V? V is nothing but, we have taken in parallel plate minus as initial, and so this is minus as initial and this positive as final, correct? Please remember all these things. So our formula was minus plus or initial final E ds. Here ds is nothing but minus dr, because this is opposite to your this thing, radial direction. Radial direction is like this, and we are taking from minus to plus. So this will be, so naturally this will be minus this. This will minus is nothing but A. Sorry, it is B. This is A, and E we can take outside because it will be uniform, and it is your dr. Sorry, E is not uniform. E we can write it. E we can write it from here. Q upon epsilon 0 2 pi r L and dr. Please understand this, because here E is changing with respect to R. So we have to take this account for finding out the voltage. And this will give you your Q upon 2 pi epsilon 0 L, and take these limits. This is 1 by R, dr by 1 by R, so this will become log. This will be log B. Basically it is log. Now it can be rearranged. Q is equal to 2 pi epsilon 0 L upon log V upon A is into V. Correct? What is this? This is nothing but Q is equal to CV. Q is equal to CV. So C is nothing but this. So C here, in case of cylindrical capacitance, is 2 pi epsilon 0 L upon log B upon A. Any problem? So you have to see, if parallel plate capacitor is there, C's values is different. If the cylindrical capacitor is there, then C's values is different. It depends on the geometry of the capacitor. Here also it does not depend on Q or V or anything else. Okay. Now let us see a spherical capacitor. A spherical capacitor, again, if you see the cross section, this is the inside sphere and this is the outside sphere, and same way it is A and it is B, correct? So here E epsilon 0 into E into A will be the surface area of this. Suppose this is the Gaussian surface. This is plus, minus, correct? So this is the child enclosed, and this is a Gaussian sphere basically. This. So it will be nothing but pi 4 pi r square, because this is r. Nothing but Q or E will be Q upon epsilon 0 4 pi r square. Same way, here V will be your minus 2 plus. It will be Q 4 pi epsilon 0 dr upon r square, because it is E into ds. ds will be minus dr, so naturally it will be minus. Now, if you integrate this, then you will get this formula as Q upon 4 pi epsilon 0 d minus A upon AB. From here, what will be your C? If we CQ, naturally your Q is equal to CV. So naturally C will be nothing but 4 pi epsilon 0 on AB or B minus A. So this is in case of spherical capacitors. So if we change the geometry, then formula for capacitance also changes. You have to see. Now we can see, suppose we take the surface, the outer sphere, to infinity. What will remain? The inner sphere will remain. this is the example. Our Earth is like this. It is the inner sphere. Outer sphere is at infinity. So in such case, this Earth behaves like isolated spherical capacitor. This is what the example I gave you in the beginning, that Earth behaves like an isolated spherical capacitor and it has charges. And the charge burst occurs during the lightning. What will be the capacitance of this isolated sphere? Here, what we assume, this B is going to infinity. So in this formula, C 4 pi epsilon 0. Suppose if you write it as A 1 minus A upon, correct? We can write it as this thing. Now B is going to a sphere, sorry, infinity. This going to infinity means what will happen? This will be nothing but 4 pi epsilon 0 A, or we can write it as C is equal to 4 pi epsilon 0 R. What is R? R is basically the radius of the Earth. So this is how we can find out the formula for capacitance in case of different type of capacitors. Now we will see this parallel and series capacitors, and in this case what happens was you have a circuit, you have one capacitor like this, another capacitor like this, and third capacitor like this, and this is these capacitors are basically they are joined in parallel. Suppose this is C1, this is C2, and this is C3. But here let us see, whatever V is there, this terminal is attached to all these V equally. Means these capacitors are at equal potential. Correct? But naturally, because of this capacitance is different, so your charge accumulation or charging will be different. Means your Q1 will be how much charge will be there, C1 V. Your Q2 is nothing but CT V, and Q3 will be nothing but C3. Like that, these are the charges, they will be accumulating on this. So total charge is how much? Q is equal to Q1 plus Q2 plus Q3, or we can write it as V into C1 plus C2 plus C3. Now, what is this Q upon V? Q upon V is nothing but your C. Now C is C equivalent. This will be nothing but Q upon V here will be nothing but C1 plus C2 plus C3. So like that, if you have n number of capacitors are attached in parallel, then their sum will be the total sum will be the equivalent capacitance, and this is same as like this. Correct? This is the same as this. Instead of having this, all these different capacitors, you can have this. It will give you the total charge from this. So when they are connected in parallel, then this is the formula. You can calculate the C equivalent, means what is the equivalent capacitance of the all three capacitors. Now let us see if they are connected in series. Let us correct the capacitors in series. Capacitors are denoted by this sign like this. Now this is how they are connected in series. Here C1, C2, C3 capacitors are there, and here V. So in this case, what will happen? Naturally, this terminal is connected here, then different terminal is, so it will have voltage different but charge as same. Means it will have charge. The charge will flow same, but voltage will be different here. Correct? And this voltage will be nothing but this same. This we can write it as Q upon C1 plus Q upon C2 plus Q upon C3. Correct? So V upon Q is equal to 1 upon C equivalent. This is nothing but 1 upon C1 plus 1 upon C2 plus 1 upon C3, or we can write it as correct. Suppose n number of capacitors are there in series, then their equivalent capacitor you can calculate like this. So we have covered in this chapter what was capacitor, how we can charge the capacitors, what type of capacitor, and we have seen different type of capacitors. We have derived a different formula also for finding out the capacitance, and what is isolated spherical. We give you some idea. Now these two very important things are remaining, because this is also very large, because this dielectric substances are there, then atomic view is there, and what happens when dielectric substances are inserted between the parallel plate capacitors, and this is how they are inserted, and if they are in series, they are in parallel, how this formulas changes, like that, all those things. Because this is a very long, this is also very long topic, so we will cover in our part 2 video within 1 or 2 days. So this was all about the capacitance, except energy, this is very important, and dielectrics, that we will cover in the next video. Thank you very much. If you like this video, please subscribe my channel, and we are going to cover like this the whole electricity and magnetism chapter and the other chapters of class 12 first, then we will come to the class 11. Thank you very much.